Hello guys, today we're going to be covering section 3.1, derivatives of polynomials and exponential functions. But really we're going to be starting chapter 3 today, which is just more differentiation rules. So we introduced derivatives, how to find derivatives, some notation for derivatives. But now we actually have to get into like the meat and bones. Kind of like what we did with limits. Once I kind of introduced you what limits are, how to work with them a bit, I showed you some of the limit laws. So today we're going to be going over the instead of limit laws, we're going to go over differentiation rules. So different ways you can differentiate functions, and find out what the derivatives are. So the first thing we're going to start off with is just like a constant function. All right, so let's just consider, the function f of x is equal to some c, so a constant. C is just a number, it doesn't really mean it, and no number specific, but just constant function. If you want to find out its derivative, so f prime of x, so this is just going to be, if you remember the, let's see, the definition, it's going to be f of x plus h minus f of x divided by h. So we have the limit as h goes to 0. And one of the things that we get is that, f of x is constant, so it doesn't matter if you go to x or x plus h, you just get c minus c divided by h, which c minus c is just 0. So you just do the limit as h goes to 0 of 0. Therefore, is equal to 0. So that's not too hard. So one of the things that we get, the result of this, is that any constant function and I'm going to be using slightly different notation whenever I told you about the two different notations that we'd be using. So whenever I write these definitions of derivatives, so you could write c prime, which, honestly, that's kind of hard to understand what you're doing. And if you're having something complicated and you try to just put that there, it may not be easy to follow what exactly the person is doing. So that's why one of the notations is we use d of dx of c. So this would be like, c is the arguments or whatever it's taking derivative of. And what we just shown above is that it's equal to 0. So I'm going to mark that in red because it's important. So that's pretty nice. That's a pretty easy thing to start with. So we can keep on continuing with this, What if we let f of x just equal to x? So in this case, we can find f prime of x as usual. So f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x divided by h. Okay. Same thing as above, we're just going to plug in f of x plus h minus f of x, so we just get x plus h minus x divided by h, which is equal to the limit as h goes to 0. We just get h over h, which is just equal to 1, because these will cancel. So we just end up getting that to equal the limit as h goes to 0 of 1, which is equal to 1. So again, what we got is the derivative of x is equal to 1. So far this is, going pretty nicely. It's not too bad. It's pretty nice. Finally, let's consider another function where we can find its derivative, where it's going to be able to form if this wants me right. Okay, sorry, it's being funky. All right, so finally let's consider f of x is equal to x squared, and we want to find f prime. So, again, so we got was, f prime of x is equal to the limit as h goes to 0 of, I'm just going to go ahead and jump to the depth, after we plug in the function. So x plus h squared minus x squared divided by h, which is equal to the limit as h goes to 0 of, let's see, what was it? X squared plus 2xh plus h squared minus x squared divided by h. And then we have some terms that will cancel. So namely, these will cancel, leaving you with just 2xh plus h squared divided by h. And then, those h's will cancel, leaving you with just 2x plus h. And then when you take the limit as h goes to 0, the h will go to 0. Therefore, you just get 2x. So what we get was that d of dx of x squared is equal to 2x. So we can continue going down this route and proving every possible integer power we could. We could keep on doing on this route and get like x cubed. Then we could do x to the 4th, or we could do x to the 1000th. But there's an easier way to do that. Or, you just acknowledge one of the rules that you can prove. If you want us to be more general, what we could do is instead of saying, f of x, equals to x to the x squared, we could just do x to the n, where n is a natural number, and then do that instead. But, let's just trust me, I did the math. So what we're going to get is a thing called the power rule whenever we try to prove that. So let's just say if n is a positive integer, so again, this is like n is equal to 1, 2, 3, and so on. Like your counting numbers, as some people call them. Then you have d of dx, the derivative of x to the n, is equal to n times x to the n minus 1. So what this did is that we brought down the exponent and then subtracted by 1. So I'm just going to write that kind of like informally, just write it in blue on how we usually say like a derivative of the power rule. We'll say bring down the exponent and subtract 1. So that's just one of the kind of ways you could just say the rule and kind of memorize it. But let's do a quick example of what this might look like. Let's just say we wanted to do the derivative of, d of dx is equal to x to the 1000th. So then what I said is bring down the exponent. The exponent is 1000. And then subtract 1 from the exponent, so 1000 minus 1 to equal 1000 times x to the 999. And we can kind of confirm that with some of the stuff we've done before. Right here, this was, our n is equal to 2. So n is equal to 2, so we bring down the exponent, we get 2, then we get x to the 2 minus 1, because bring down the exponent, subtract by 1, and we just get 2x to the 1, which is what we got. And you can kind of attest that it works with the other previous examples we did. So far, this is a pretty nice rule, honestly. But I haven't told you how the derivative works over, a few different, cases. So right now we're only working with, the positive integer cases, but it might not, one of the things we've done previously was that we did d of dx of, the square root of x, and, which is the same thing as, and this is one of those important things that we're going to have to touch upon, is you have to learn how to rewrite your x's as, as to their, numerical powers. So I usually, when I see the square root of x, I don't really think the square root of x. I really think x to the 1/2. So one of the things we've done before was we got this as 1/2 times this, whoops. I love when that happens. It's 1/2 times, 1 over the square root of x, which is equal to 1/2 times x to the negative 1/2. And if you're a bit rusty on your exponential skills and all that, I would just be a bit mindful of, especially when it comes to the power rule and all that kind of stuff. And then, it's very easy to just try to rewrite things with the numbers for exponents instead of using radicals or any of that kind of stuff. So if you kind of look though, here we had x to the 1/2. Here we brought down the exponent and then subtracted by 1. Just so you know, 1/2 minus 1 is equal to negative 1/2. So just that one. So actually, we can do the more general power rule now. Where it doesn't have to be a positive integer anymore. So if n is any real number, or, as trying to get you guys used to the notation that n is an r, and then we have dx of x to the n is equal to n times x to the n minus 1. So it's the same thing as above. But this case actually allows us to be more general and talk about, different sort of cases. So let me just mark that in red. All right. So let's keep going. Or no, let's keep going. Let's do an example real quick. I'm stupid. All right, let me do this, keep that right there. So let's, differentiate y is equal to x squared times cube root of x. All right, so some of you guys might say, what are you doing? Because you haven't told us how to differentiate, what happens when you have two things being multiplied together. But this is where, knowing your exponent rules is very helpful. So here we have, y is equal to x squared times the cube root of x, which is equal to x squared times x to the 1/3, which we can just add the exponents together. So we just get, 2 plus 1/3 is equal to, just 7/3. So we just get x to the 7/3. And now we can use the power rule, or the general power rule. So again, this notation, if you haven't seen it before, it just means implies or it follows. So y prime is equal to 7/3, because we brought down the exponent, times x, and then 7/3 minus 1. So it's equal to 7/3 x to the 4/3. Yes. And that's just the way we use the power rule, the general power rule. And this works with a lot of cases too. It also works if we have the case, x to the negative 2. If you want to find d of dx of x to the negative 2, bring down that exponent, subtracted by 1 to get negative 2 times x to negative 3. It works with the negative exponents as well. But, that's kind of the case when you say n is any real number. It covers all numbers. It's not complex numbers. All right. So there's another rule that we can use. It's called a constant multiple rule. As you can probably guess, it was pretty similar to what we did with the limit. So if c is a constant, and f is a differentiable function, then this is what we have. So we have d of dx of c times f of x is equal to c times d of dx of f of x. And then we can write that in terms of, like prime notation. Because, sometimes it's a bit easier to write it like this. We say, the derivative of cf is just equal to cf prime. So basically what this means is we can pull out constants from the derivative. Like if you multiply like a function, by a constant, then that's not going to be changing its derivative. It's just going to be that constant times the derivative. So that's pretty nice. So all right, so let's keep going. Let me just double check something real quick. Okay, sorry, I was just double checking something. Some notes have proof of that and some note. You're welcome to double check this stuff yourself, like if you wanted to prove this, you can prove it. This is like, if you want to show that, this is true, you can actually use the limit definition of a derivative and actually prove this for yourself. You just have to do, g of x is equal to c times f of x, and you could find the derivative of that, and you would just get it equal to kind of what we had above. Just the derivative of f of x times c. All right. Now here comes to the kind of cooler ones that we like to use. Okay. So now it's going to be the sum and the difference rule. You don't really need to say the sum or difference rule, because in mathematics, really just like subtracting two numbers is just adding a negative number. So that's why, it's a sum difference rule, but we kind of talk about them as if they're the same. So basically they are. All right. So what, f of x and g of x be differentiable functions, because again, when we talk about these rules, we need nice enough functions. Oops. Then what we get, we have d of dx of, f of x plus g of x is equal to d of dx of f of x, plus d of dx g of x. So basically what this means is that you can break up, the derivative over a sum. And again, in terms of some of the other notation you might see is f plus g prime is equal to f prime plus g prime. Oh, let me just... So you're welcome to write it kind of either way you want. It's just you just kind of have to be wary of just like how your equation looks, because you're welcome to write both. But if someone's looking at a very complicated equation and you're just writing a bunch of primes over everywhere, then it may be messy and hard to read. So you just have to keep that in mind. So likewise, so we just had the sum rule, because this is the sum. The derivative of a sum is equal to the sum of the derivatives. Kind of like the same thing we did with limits. So then, also like what we did with limits, where we have the difference rule. So the derivative of f of x minus g of x is equal to d of dx. So the derivative of f of x minus the derivative of d of dx or g of x. So basically the same thing as above, but now one of them is negative. And again, in terms of like the notation you could say like f of minus g prime is equal to f prime minus g prime. All right. So these are pretty nice. So, I could do a quick example real quick, but it's kind of more definitions what we're doing. So maybe I'll just do like a quick example, just kind of blow through, but I'm just going to do it fast. Mostly because we still have other things to touch upon. So let's just say we want to do the derivative of, find d of dx of, 5x to the fourth plus 3x plus 2. All right. So you kind of notice that here we have three functions. We have this one right here and this one right here and this. So I'm going to use, the fact is that, the sum rule talks about two different functions at once. But you can work around this by saying this is your f of x and this is your g of x. And then just, and then whenever you find d of dx, you do, here's your second function, here's your first function, or whatever. The fact that there's three isn't really a big deal, because you could just call the first two parts equal to your g of x, if that makes sense. All right, so again, I'm going to try to blow through it real quick. So 5x to the fourth plus 3x plus 2. So the derivative here is, the first thing we can note is, kind of similar to what I just said. You can break up the sum over, you can break up the derivative over the sum. You get 5x to the fourth plus d of dx, 3x, then plus d of dx of 2. So then it's going to be equal to, so remember the derivative of constant is equal to 0. And whenever we did, if we had a multiple or like a constant out front, we can pull it out. So this is equal to 5 times d of dx of x to the fourth plus 3 times d of dx of x plus 0. And then lastly, we get 5 times the derivative, so it's x to the 4, so it's going to bring down the 4 times x to the 4 minus 1. So that's just going to be 3. And then for the last one, it's going to be 3 times, kind of like what we said before, we actually found the derivative of d of dx of x, or we found the derivative of x already. So it's equal to 1. So we just get 20x cubed plus 3. And that's our derivative. So whenever you find these derivatives, you don't necessarily need to break it up as what I did and, use all the laws now. Kind of like what we did with limits. You just have to make sure that, each step you're doing is valid and is backed up by a limit law. And if you can do that, then you're welcome to, skip a few steps. That's fine. But, that kind of is just like, it's not really a big deal. It's similar to the limit laws, basically. But now we're working with derivatives. All right. So the first thing we need now is the definition. Kind of like what we talked about, tangent curves and all that. We also have a new notion of, a new thing we can work with called normal lines. So definition. So the normal line of a curve, to a curve at a point P. Let's see, is the line through P and that's going to be perpendicular to the tangent at P. All right, so that's a little funky. So what I'm going to tell you, like, all right. So just, some shorthand of what that means is that, so for tangent lines, what we had was you have, the point, you had a point P, which is equal to like, x1, y1, and then you had your slope, the slope at, P, of like, the curve that we're talking about is usually, if you usually define it in terms of like, f of x, would be like f prime of x1. So basically it just means, the slope of the tangent is equal to the derivative at that point on that curve. And likewise, for normal lines now, we still have the same point. You have P is equal to x1, y1, and now our slope is equal to the negative 1 over f prime of x1. Because that's what it means to be perpendicular. You do the opposite and the reciprocal. So the opposite means the other sign of it. So if it's positive, it's negative. It's negative, it's positive. Here, this is positive, so it would be negative, and then you would divide by it. And this is assuming it's not equal to 0, but if it is equal to 0, then you have to do something a bit different. So let's just do an example. This example is going to be a bit complicated, but it's going to be, find the points on the curve, so y is equal to 2x cubed plus 3x squared minus 12x plus 1. See, we have where the normal line is vertical. So one of the things I should mention is just like, so tangents don't actually kind of relate to derivatives, but if we have a nice enough function, then we can talk about them in terms of derivatives. But, a tangent line can easily just have like a hump right here. Like if we had a curve and then the tangent line at just like this peak would just be a horizontal line. And that means that the normal line, so this was, if this was a tangent right here, then that, normal line would be like a line. I'm going to try to draw the same picture. The normal to that will be a vertical line. So the vertical line only happens, the normal line is only vertical if the horizontal, or like the slope of the tangent, is equal to 0. All right. But again, this is a more special setting, but now we can try to figure out what's going on. So if you remember, the tangent line is the horizontal. So remember kind of what I just said right here is that the slope at P, the slope at, the tangent line is equal to f prime of x1. So if it's horizontal, then that means it has slope 0. So in this case, it would be 0 for us. So because we're really working with a case with the tangent is horizontal, means that we want cases, our x values such that our derivative, f prime of x, or y prime of x actually, is equal to 0. All right. And that's kind of what it means, and that's another way of saying, if something is like horizontal, if you have a horizontal tangent, that means the derivative is equal to 0 at that point. So let's go ahead and find the derivative now. So we had y prime is equal to d of dx of, let's see, it was 2x cubed plus 3x squared minus 12x plus 1. And then keeping with track of, what I've did before, but instead of having to write everything, I'm just going to take the derivatives all at once. So again, was bring down that 3, then subtract, 1 from the exponent to get 3 minus 1 is 2, plus 3 times bring down that 2 times x to the 2 minus 1, which is just 1. Then minus 12 times 1 times x to the 1 minus 0, which is just 0, so it's 1. So plus 1. Well, nope. The derivative of a constant is equal to 0. My bad. So that's it. Actually, let me just write it down just to be clear. All right. So then all we have to do is now is just simplify. So we get 6x squared plus 6x minus 12. So you can pull out that 6. You get x squared plus 1 minus 2, which is equal to 6 times x plus 4, x minus 3. So remember this is equal to y prime. We want y prime equal to be 0. So thus this is only equal to 0 when x is equal to negative 4 or 3. Because that's just kind of one of the properties of just like if you have something like this equaling to 0, then either this is equal to 0 or this is equal to 0. So I already plugged in those points, plugged in the y values. So we actually have the points, negative 4, negative 127, and the other point was 346. So at these points, the normal is actually vertical. All right. So then we're just covering one last kind of derivatives, which is going to be the derivatives of exponential functions. All right, so one last case is going to be derivatives of exponential functions. All right, so now we're going to let a function be, f of x is equal to a to the x, which is a very general form of a exponential function. So using the definition, we're going to try to figure out what we get. You get f prime of x is equal to the limit as h goes to 0. Again, it's f of x plus h minus f of x divided by h. And this is going to be equal to the limit as h goes to 0 of of a to the x plus h, because now it's x plus h is in, x is in the exponent of a. So x plus h would also be in the exponent of a, minus a to the x divided by h. And now I'm just going to simplify. So again, we have the limit as h goes to 0. We're going to pull out, and we're not going to pull out anything yet. We're going to break up the, the exponents. We get a to the x times a to the h minus a to the x divided by h, which again is equal to the limit as h goes to 0. One of the things we should notice now is that, a to the x is in both of these terms. So before I even write the limit, I'm going to pull out these terms, a to the x. Get a to the x times the limit as h goes to 0 of a to the h minus 1 over h. And the reason you can do this is because you can only pull out things that don't depend on h. So a to the x has no h. Yeah, and basically, like, if you have like two kind of letters that you're working with, and one of the things, like in this case, if we do the limit as h goes to 0, the limit only depends on, the limit is only telling you what h does. So if you have basically like two letters, x and h, ignoring that a is supposed to be like a letter at the moment, but if we're having two things that we're kind of we're doing things with, we're allowed to treat one of them as a constant, basically. That's why we get to pull out that a to the x. So, if you guys remember, what this looks like? What if the case, x is equal to 0, then we get, a to the x plus h, or 0 plus h, minus a to the 0, which is equal to a to the h minus 1 over h. So this is actually, the derivative of f of x at 0. And you can double check that with the definition, just to be clear. So what this gives us is that is equal to, f prime of 0 times a to the x. So you get that the rate of change of any exponential function is proportional to the function itself. Oops, f prime of x, okay. Alright, so that just means, the rate of change of any exponential function is proportional to itself. Well, basically it just means that functional. It just means that when you take a derivative of, when you find f prime of x, you just get the function itself times, just some constant. In this case, the constant is just f prime of 0. So one of the most sexiest exponents we're going to work with, one of the most sexiest numbers is e. So e is a number such that, we're going to have the limit as h goes to 0 of e to the h minus 1 divided by h is equal to 0. Not equal to 0, my bad, is equal to 1. So in the case above, that was basically saying f prime of 0 is equal to 1. Like in terms of, what this graph looks like, if I'm going to do the graph of e to the x. E to the x. And this will be that'll be 1. No, is that all what I wanted? In the tangent line, we'll have slope 1. All right. So that's basically just one of the ways to define E, but when we talk about that in terms of, the derivative, let's talk about how this kind of relates to the derivative, is that the natural exponentiation function the derivative of the natural exponential function. So the natural exponent is typically we say is e. Usually if we say like a natural exponent, we just say e to the x or something like that. Because e is kind of one of those very nice numbers, and you'll see why. We have that d of dx of e to the x, oops, so really big E, is just equal to e to the x. So this is why it's referred to being as like natural, is because when we take a derivative of e to the x, we just get back e to the x. So nice, very sexy, very beautiful. So one last example to work with this is we're going to do, like given f of x is equal to 2 times e to the x minus 14x, you want to find f prime and f double prime. So f prime of x is going to equal to d of dx. I'm going to go ahead and break it up over, the difference. So 2 times e to the x minus d of dx of 14x, which is just equal to, we can pull out the constants d of dx of e to the x minus, you can pull out that 14 d of dx of x okay, hopefully that's not too messy. Will just be equal to 2 times e to the x minus 14. So that'll be equal to f prime of x. And then lastly, you have to do f double prime of x, which is going to be equal to d of dx of, now we're going to take a derivative of f prime of x. You get 2 times e to the x minus e of dx of 14, which just equals to, again, we pull out the 2, find the derivative. Again, we just get 2 times e to the x minus 0, because the derivative of constant is equal to 0. So we just get equals to 2 times e to the x. All right, so that's pretty much it for this section. I was looking over the homework real quick, and it was like, one of the problems was like, find a normal, find the equation and find a normal line, like with respect to, it was like y is equal to, I want to say like x squared minus 8x plus 7 parallel to like x minus 2 y is equal to 7. I just want to kind of work on this problem real quick because that was the only problem I saw that was like a little strange. So, again, that we want is a normal, remember, like a normal line is something that's going to be perpendicular to the tangent. So the first thing we need is, to find this normal line is, we need the slope. We'll say at the point, we need a point, like, okay, to find a normal line, we need a slope. And a point. So the slope will come from the fact that it's parallel to a certain thing. You know, it's parallel to that line. So we get x minus 2y is equal to 7. I'm just going to rewrite that. I'm going to solve for y. So, you know, get x plus 7, well, x minus 7. So move the 7 to the other side and then divide by 2. So we get like y is equal to x over 2 minus 7 over 2. And then the slope of this line, which you could just take the derivative of, and you get it equal, and you get to 1/2. So we got the slope of the normal line is equal to 1/2. So the tangent line that's going to be, you know, perpendicular to the normal line. Remember, it's perpendicular, so it's going to be, you know, the opposite over, and the opposite and the reciprocal. So we just get negative, then the reciprocal of 1/2 is just 2. So negative 2. So then we just get y's. So then we talk about, you know, our curve right here with respect to, you know, this right here, like the curve they actually want to find a normal line with respect to, we have to do, you know, y squared is equal to x squared minus 8x plus 7. So we need to find the cases where the derivative of that is equal to negative 2. So you do y prime is equal to 2x minus 4. Well, not 2x minus 4, it's 2x minus 8. And then what we have to do is, you know, find the tangents or find the x values actually give us negative 2. So we get 2x minus 8. Add 8 to both sides, divide by 2, and we get x is equal to 3. So then we just need to, you know, plug that into here, and that would give us our m, which is equal to negative, well, just equal to 1/2. And our point P will be equal to like 3 of whatever we get, you know, into here. All right, I love when that happens. It just, you know, jumps all the way up there. All right, and then from there, all you have to do is just plug it into like a point slope form, like formula or whatever. So this section wasn't too bad. It's just more, you know, differentiation rules. But I think that's it. You know, like, comment, and subscribe, I guess. I'll see you in the next one.